Hello again, Chem 20s. Today we are going to talk about acids and bases in terms of their pH, which I'm sure you've heard of before, and their pOH, which you probably haven't heard of before. So we are currently on page 16 of the acid-base section of our solutions workbook. You might be wondering what happened to page 14 to, well, 16 up above here. We're not going to do that at all. You will revisit that 100% in Chem 30. And as a matter of fact, that page 14 to 16 is just some, even during regular class time, just some bonus material that to start you getting ready for Chem 30, but again, not at all necessary. You will totally 100% be retaught that. So what we want to look at is page 16, pH and pOH. Anything from here on in is exactly what we're looking at. So jumping into it, what is acidity and what do we mean when we talk about acidity? Well, realistically, we are going through and talking about a couple extremes from chemicals and extreme natures of chemicals. Exactly the same way that we can often describe temperatures in terms of extreme, like hot and cold, and you can have really hot and like really cold. We can have really acidic and really basic. And just like with when you take hot and cold water, this is all in this first section, by the way, here. Really, really hot water, really, really cold water, you put them together, they kind of even out. They neutralize each other. Same thing with acids and bases. You can take something that's ridiculously acidic and ridiculously basic, and they will neutralize each other. Another important definition, you already know this one. Something that is not acidic or basic, you call that one neutral. So yeah, jumping in, we've got pH of 7 is neutral, less than 7 is acidic, and greater than 7 is basic. Cool, so we've got to talk about that a little bit. Now, one thing that is in this last little section here, and it kind of jumps onto the other page too, which is a little bit annoying, is that the pH scale, while it does go 1, 2, 3, 4, all the way up to 14, a jump of 1 on our pH scale is actually not like 1 times more acidic, or a jump of 2 is not 2 times more acidic. For every jump that we see on our pH scale, we are 10 times more acidic or 10 times more basic. So let's just write a couple of these out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and I'll do 14 really small in the corner over there. So we know that 7 is neutral. I'm just going to put N for neutral there. And the closer to 1 we get, the more acidic we are. And the closer to 14 we get, the more basic we are. Cool, okay. So now what I'm talking about here is if I went from something from, what does the example say here? From 4 to 5. So if I went there, from 4 to 5, it's actually 10 times more acidic. So a jump of 1 on this pH scale is 10 times more acidic. But if I went from 6 to 4, so I'm going from 6 to 5, well, that's 10 times. And then I'm going from 5 to 4, so if I went all the way from 6 all the way over to 4, that's 10 times 10, that is 100 times more acidic. So you can see how this grows really, really, really quickly. Something with an acidity of 1 is significantly more acidic than something with an acidity of 6, on the scale of like millions of times more acidic. Cool, so I hope this makes sense. We could talk about this. Actually, you know what, let's do an example on the other side as well with basic. So let's say if I had a solution with a pH of 8, and I wanted to figure out how many times more acidic something with a pH of 12 is. Well, that's 1, 2, 3, that's 4 jumps. So that's times 10, times 10, times 10, times 10. So that's 10 times 10 is 100. Times 10 is 1,000, times 10, that is 10,000 times more basic, which is pretty wild. Like it jumps quickly. Cool, so the top part just kind of finishes off talking about what we were just talking about. Now, as we go through, we do need to talk about the concentration of H3O, that's hydronium, and OH, that's hydroxide, because those are what tell us our concentration, or sorry, our relative acidic and basicity. So One little issue with this is that they're usually very, 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 very extremely small numbers. So concentration of 10 to the power of negative 7 moles per liter, for example, is neutral. Concentration of 10 to the negative, say, 14 moles per liter of H3O is very basic. So very small, 10 to the negative 7, 10 to the negative 14. Sorensen, 1909, came up with kind of a more practical thing called the pH scale, and this is where it comes from. So pH of some common things, you can take a moment to check this out in your booklet. Everything from gastric juice in the stomach, so that's your stomach acid, with a pH value of 1 to 2, to urine, 4.8 to 7.5, to saliva, about 6. Those are all acidic, by the way. Pure water has a pH of 7, so completely neutral. Blood, did you know blood was slightly basic? Household ammonia, so the stuff that you clean with, typically 11.5, so quite basic. So it's a little bit easier to describe, right, than times 10 to the power of negative whatever moles per liter as our concentration of hydronium ion. Quite a bit easier to describe with that pH scale. Oops, didn't actually mean to do that. So what does pH actually mean is a question. It's just simply a way to express hydrogen ion concentration in solutions at 25 degrees Celsius. So essentially tells us how acidic or how basic they are. If you really want to know, it means power of hydrogen. And we're actually looking at the 10 to the power of whatever in those concentrations. Cool, okay. So let's see here. Yeah, there we go. So we got a little well, a little idea here to look at. So if I have an acidic solution, you know that we have a pH less than 7. But did you know that we have a concentration of hydronium ion greater than 10 to the power of negative 7? Cool. Neutral solution, we already knew that the pH was 7, so that's no problem. But you have a concentration of hydronium ion equal to exactly 1 times 10 to the negative 7 moles per liter. And then finally, we've got a basic solution. With a basic solution, we've got a pH greater than 7, and we've got a concentration of hydronium ion less than 1 times 10 to the negative 7. So we can kind of go through and start to see some patterns here, right? So the smaller the pH value, the greater the concentration of hydronium ion. And that makes sense because hydronium ion is what makes things acidic. The, excuse me, the greater the pH, the smaller the concentration of those hydronium ions. And one thing that, I guess this is the one thing from that previous section on page 14 to 16 that we should have known, is even neutral substances have some OH and some, oops, H3O. It's just their concentrations cancel each other out perfectly. So even neutral substances have that. Cool. Okay, so pH meters, pH paper, different indicators all give us different pHs from 1 to 14. That being said, I think we talked about this before, you can have acids that are stronger than pH 1 and bases that are stronger than pH of 14. We're not going to use them in high school ever, but maybe one day depending on where you get to. Cool. Anyway, so again, another little chart to help us describe that. One thing that I want you to look at, and I'll get you to put the video on pause for a second or two here, is these couple questions right here. We've talked about a couple different ways to identify whether something is acidic or basic. This is essentially what we're looking at. Can you identify if this is acidic, basic, or neutral based on pH and concentration of hydronium ion? So I'm going to do the first one with you. I've got 2.4 times 10 to the power of 5 moles per liter. We said that 10 to the power, and it was actually 1 times 10 to the power of negative 7, was neutral. And of course, that's moles per liter. We said that if it's got a larger concentration than that, then it's going to be acidic. So the question is 2.4 times 10 to the negative 5 a larger concentration? And lots of people get confused because they're like, oh, well, 5 is less than 7, so no, it's not. but this is 10 to the negative 5 versus 10 to the negative 7, and this is actually a greater concentration. So this is actually going to be acidic. So when we're dealing with those negative exponents that we've got up there, the less negative it is, the bigger the number is. And I'll just give you a quick example here. So 10 to the negative 2 is actually 0.0, and I'll make it a little bit easier. 1 times 10 to the negative 2 is 0.01. If I had 1 times 10 to the negative 4, it would actually be 0.0001. Now, which one of those two numbers is bigger? Obviously this one, right? Obviously that one. So again, put the video on pause here. See if you can see if you can figure out the answers for these questions here. I will do the same, put it on pause, and we'll compare notes in a moment. So if you haven't already, go for it. Alrighty, so I'm back. I've got acidic, B is acidic, C is acidic, D is basic, E is basic, F acidic, G neutral, and H base for acidic. So I just summarized: A is acidic, B is basic, and N is neutral. So hopefully your answers check out. That might be something you want to ask about next time we meet if they didn't. Okay, next piece that we want to go through and talk about, again, is talking a little bit more about pH and how we can go back and forth between the concentration of hydronium ion and the actual pH. So what corresponds to what? We've got a couple of those values. We've already talked about how like a pH of 7 has a concentration of hydronium ion of 10 to the power of negative 7. We've actually got this formula. I don't know why there's an extra bracket in here, but we've actually got this formula that can tell us, if we know the concentration of hydronium ion, it can tell us the pH. So the formula, and this is a formula that you need to memorize, absolutely should have memorized, pH is equal to negative log times the of the concentration of hydronium ion. Cool, now that sounds fancy and scary, and if you haven't done logs before, it might be, but we're doing a super simple version of this. You can look forward to, I believe it's Math 20-1 or 30-1 where you do logarithms and logarithmic scales, but for now, the easy version. So let's check it out. Let's see it in action, this formula. So you got the concentration of H3O in a bottle of table wine is 3.2 times 10 to the power of negative 4 moles per liter. I'm just going to make a little note. That's acidic. That's less than 10 to the power, greater than 10 to the power of negative 7. So that's actually acidic. So hopefully we're getting something like that. Okay, right after the cork was removed, only half of the wine was consumed. Oh no. After it had been standing in the open air for a month, the hydronium ion concentration was 1 times 10 to the negative 3 moles per liter. So that's more acidic. We want to calculate the pH of the wine on both of these occasions. So new wine, let's call it new wine. We've got our formula. The pH is going to be equal to the negative log of the concentration of hydronium ion, and the concentration of hydronium ion, remember that's what the square brackets means, let's see, was 3.2 times 10 to the negative 4 moles per liter. Cool, okay, I'm gonna get out my calculator. I hope you do the same. You need a scientific calculator for this one. So I'm gonna turn it on. I'm going to go through, oops, I think I pushed that too many times. I'm going to push my negative button, not minus, my negative button. I'm going to push log, which on these calculators is right beside the number 7. So negative log 3.2. And some of you are going to be familiar with this second function, e. That just means times 10 to the power of whatever comes immediately after it. So 3.2 times 10 to the power of negative 4. I hit enter, and that gives me a pH of 3.494850022, which is way too many significant digits. There's a new rule for significant digits, by the way, which is over here. So my concentration, that's just a regular plain old number. I've got 2 significant digits. 2 sig digs in each of these. For pHs, here's where it gets a little tricky. For pH, only the digits to the right of the decimal point are considered significant. So for example, 8.29 has 2 significant digits, whereas 3, there's nothing after the decimal place, has no significant digits. So pH of 8.29, that's 2 significant digits. Only after the decimal place counts. So when I go back to, let's check this one out, I'm allowed 2 significant digits. This is going to be equal to 3.49. You'll notice that there's no units, and this is 2 significant digits. 2 sig digs to match up top here and here. Cool. So it's not too bad, right? Pretty easy to plug in. Maybe I should actually show you another way to have a look at this. If you're not so familiar with that second function e, that's the best way to use it in your calculator, by the way. Let's check out the other one, and I'll show you another way you can look at it if that wasn't quite up your alley. Okay, let's look at the old one. The old one. So if I wanted the pH, it's going to be negative log of 1.0 times 10 to the negative 3 moles per liter. Okay, let's go ahead and plug this in our calculator. So I'm going to again push negative log of 1.0, and in this case I'm going to do times 10 little hat thingy negative 3. This is another way to do things. It's not exactly the best way to do things, but it will work for Chem 20. So I hit enter, and that gives me a pH of 3, but I need 2 significant digits, so it's actually a pH of 3.00, because again, I want 2 sig digs. Wonder how that sits with people. Pretty good, I hope. Pretty good. So all it really is plugging this into and knowing the formula. It's not the hardest thing we've ever done, that's for sure. Let's check out number 2 here. What is the pH of a 0.015 mole per liter nitric acid solution? Knowing that nitric acid is a strong acid, we're going to look for a fairly low pH, right? Strong acids should have fairly low pHs for the most part. So I'm going to do negative log, same thing we're doing each and every time, negative log, but I don't need times 10 to the power of anything, it's just 0.015. So there's my concentration of hydronium ion in that strong acid. So 1.82, the pH 1.82. I better make sure I rounded that correctly. Yes, 1.82 is my answer for that. Now the other thing with this, the strong acid, is that it, like my nitric acid, I'm going to get back to this. I focused on the pH a little bit more there, but my nitric acid, HNO3, is going to react 100% with water, H2O, to produce hydronium ion, H3O, and NO3. And don't forget everything's aqueous, aqueous. Well, I guess water's not aqueous, and aqueous. Cool. So if it's 100%, that means I know that this concentration is also my concentration of my hydronium ion. Cool. So that's very good. What if we wanted to go the other way here? And here's the next little piece of this. What if we wanted to find the concentration of hydronium ion from the pH? So you can probably forget about this for the time being and just focus on this one. So the concentration of hydronium ion is equal to 10 to the power of negative pH. Cool. Let's try an example. I'll show you how to plug that into your calculator. Find the hydrogen ion concentration if the pH is 12.62. So by the way, how many sig digs is this? That is 2 sig digs. Because remember, it's only stuff after the decimal place that counts for sig digs when we're talking pH. So my concentration of hydronium ion is going to be equal to 10 to the power of negative pH. So it's 10 to the power of negative 12.62. And check out how easy this is. I'm going to clear the calculator. So I'm going to do 10, this little hat thingy, or the upward arrow-ish looking thing, right above the dividing sign. 10 to the power of negative 12.62. I end up with 2.3988 something 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 times 10 to the negative 13. Remembering I want 2 sig digs. Come back here. That should be 2.4 times 10 to the power of negative 13 moles per liter. Cool, not so bad, right? Chem 20s, you can handle this. Fairly easy calculations. Again, you kind of need to memorize the formulas, but they're fairly straightforward. They're fairly easy formulas to deal with as long as you got them done. Okay, let's do one more. Calculate the pH of rainwater collected in a certain region of the northeastern United States on a particular day was 4.82. Calculate the concentration of hydronium ion calculate the concentration of hydronium ions in the rainwater. Holy moly, I'm having a hard time reading. Try this one on your own. Put the video on pause. See what you end up with. Go ahead, do that right now. All right, so if you're back, we're looking for the concentration of hydronium ion. We know that that's going to be equal to 10 to the power of negative pH. 10 to the power of negative 4.82. So again, I plug that into my calculator. 10 to the power of negative 4.82. Make sure I got it in there correctly. Looks good. So 1.5 with significant digits, 1.5 times 10 to the power of negative 5 moles per liter. Oops, got a little messy there, but moles per liter. Nice. Okay, so things that we're going to look at here. We are going to look at the next little piece here. If you want to do this in 2 chunks, that's a-okay. You can come back and have a look. Let's see, what are we at? So about 23 minutes. So you can come back and tune back in about 23 minutes. The next little piece, though, regardless of whether you're coming back and doing this on a different day or you're just going to plow through and have a look at the whole thing right now, the next little piece is pretty much the exact same thing that we're looking at, just now talking about the hydroxide ion rather than the hydronium ion, but same idea for the math. So you can check in on that, and please actually do have a look at, again, about 23 minutes. For now, either way, I would say put the video on pause and try out some of these questions. When you're done those questions, you can come back to 23 minutes, or you can just unpause and power through and do this all in one big lesson. Anyways, I'll let you do what you got to do now. Go for it. Okay, so we're back. We've got the practice questions, and now we are on page 21, and we are talking about pOH. So pH was the concentration on, and all about hydronium ions. pOH is going to be the same thing, but all about hydroxide ions. So it's a really convenient method to talk about hydroxide ions. pOH is totally reversed of the pH scale. So for an acid, we're going to have a pOH of greater than 7. For a base, a pOH of less than 7. It's totally flipped. So if this is a pOH scale, I've got the more acidic you go higher, and the more basic you go lower, right? And if you remember, for pH, it was the opposite. So 7 is still neutral, but we go basic up to 14, and acidic down to 1. Exact opposite, because we're talking about the exact opposite thing. We're talking about hydroxide rather than hydronium. Look at these calculations here. My pOH, you've done something like that before. It's the negative log of the concentration of hydroxide, and my concentration of hydroxide is equal to 10 to the negative pH. It's literally the exact same thing, but with hydroxide ion. Okay, so let's check out an example or two here. Determine the pOH of a solution with a concentration of hydroxide of 1.354 times 10 to the negative 5 moles per liter. Is it acidic or is it basic? Okay, so first things first, let's figure out the pOH. So the pOH is going to be equal to the negative log of the concentration of hydroxide ion. So it's 1.354 times 10 to the negative 5 moles per liter. So when we plug that in, let's just get the calculator out. So I'm going to hit negative log 1.354 times 10 to the negative 5. And no matter how you put times 10 to the negative 5, doesn't matter. You're going to end up with the same thing. Just make sure you're getting 4.868. We need, let's see, 4 significant digits. 4.8684. 8684. So 4 sig digs. And that is my pOH. That's part 1. Part 2 is it acidic or basic? Think about that one for a second. If you're thinking it is basic, you are good to go, right? Because pH scale, absolutely less than 7. The closer to 1, the more acidic it gets. But pOH is the opposite. The closer to 1, the more basic it gets. Cool. Okay. Number 6. Calculate the hydroxide ion for something with a pOH of 8.41. Is it acidic or basic? So I think in this case, it's probably easier to ask ourselves the second question. Is it acidic or basic? Well, it's got a pOH greater than 7, which means it's acidic. Again, opposite to pH. So it is indeed acidic. If I'm looking for my concentration of hydroxide ions, I would do 10 to the power of negative pOH, which is 10 to the power of negative 8.41. So I get out the old calculator, 10 to the power of negative 8.41. And this works out to be, let's see, we need 2 sig digs. So that's 3.9 times 10 to the negative 9. 10 to the negative 9 moles per liter. And again, that's for our hydroxide ion. Okay, the next example is a bit of a big one. Calculate the pH and the pOH of a solution with a concentration of hydronium ion of 2.94 times 10 to the negative 4 moles per liter. Okay, so let's go through and let's have a look at this. pH, yeah, I'm doing the right thing here, is going to be equal to 10 to the power of negative concentration of hydronium ion. So that's 2.9. Oh, no, hold on. Someone did the wrong formula here. I don't know who, but someone sure did. It's going to be negative log, there we go, of the concentration, which is 2.94 times 10 to the negative 4 moles per liter. Again, I plug that into the old calculator here. So clear, negative log of 2.94 times 10 to the power of negative 4 is 3.53. Let's see, we need 1, 2, 3 sig digs. 3.532 is our pH. Now, we might be getting kind of stuck here. So we're given hydronium ion. We found the pH. How do we get the pOH? Now, we're kind of skipping ahead here, but this is really quite big here. Really a big idea. What does that say? It says pH plus pOH have to equal to 14. They always equal to 14. So in other words, if I'm looking for my pOH, that's just really easy. I do 14 minus my pH, so 3.52, no, 3.2, there we go. So let's go back to the calculator. I'm just going to do 14 minus that answer, so that should be 10.468, I believe, 10.468. Nice. So we've got our pOH and our pH. They're always going to add up to be 14. So if you're given one, just take 14, subtract, well, in this case, pH. Hope that makes sense for people. Not too bad, right? Not too bad. So things that we've got here. This diagram is a little bit confusing at first, but it can definitely help us out going back and forth between pH, pOH, and concentrations. One thing that we're going to get rid of, this is that part that we skipped over right at the beginning of the lesson, page 14 to 16. So we'll get rid of this one and get rid of those lines. But if I wanted to go from my concentration of hydronium ion to my pH, or my pH to my concentration of hydronium ion, we know the two formulas for that, right? So from H3O to pH, we use negative log of the concentration of hydronium ion. If we want to go the other way, so I'm given my pH, and I want to figure out the concentration of hydronium ion, I use 10 to the power of negative pH. Now, if I want to go back and forth between pH and pOH, that's where I use this formula over here, right? So 10 to the power, or sorry, pH plus pOH has to be equal to 14. And then to get back and forth between concentration of hydroxide and pOH, we use pretty much the same formulas, but with hydroxide. Cool, so a handy little thing, a little bit confusing to read at first, but fairly handy. Let's look at, I believe, 3 more quick examples, and then some practice on the following pages. Okay, so question 8, find the pH of a solution with a hydroxide concentration of 1 times 10 to the negative 9. So the first thing that I want to do is I probably want to figure out my pOH. So my pOH is negative log of the concentration of hydroxide, so that's 1 times 10 to the negative 9 moles per liter. All right, let's plug it in. So I've got negative log of 1 times 10 power of negative 9. Nice, and that works out very easily to be equal to a pOH of 9. Now I know that pH plus pOH is equal to 14, so if I'm looking for the pH, well then that's just my 14 minus the pOH, which is 14 minus 9, which 14 minus 9, let's see, that's 5, pH of 5. I can do that math. So my pH is equal to 5. Cool. Nice. Let's check out number 9. Find the concentration of hydronium ion if the pOH is 11.7. Cool, so the first thing I probably want to do is, I don't really want pOH, I'd rather have pH to give me concentration of hydronium ion. So in this case, I'm going to do 14 minus 11.70. So this is going to be my pH is 14 minus 11.70. I need a calculator for this one. 14 minus 11.7. So that's going to be equal to a pH of 2.3. Next thing that I want to do, and if I'm using Signix 2.30 technically from the original up here, next thing I want to do is I want to say, okay, well my concentration of H3O is going to be equal to 10 to the power of negative pH, which is 10 to the power of negative 2.30. So 10 to the power of negative 2.3 is 0.00 0.0050 moles per liter. Nice. So in that one, we're given the pH, we can use that to find, or sorry, our pOH, we can use that to find our pH, and then from pH to hydronium ion is easy. The last one is a bit of a doozy. This one's a bit of a challenge. If you wanna tap out here, that's okay. If you wanna go, that's okay. See you later for now. This one, a bit of a challenge. It's all stuff that we've done before though. So I got 9.2 milligrams of cesium hydroxide is dissolved into 22 milliliters of solution. Determine the pOH and the pH. So cesium hydroxide, let's see. That's oh boy, CSOH. It's going to dissolve. This is going to be a strong base. This is going to be highly soluble. So it's going to dissolve totally and put CS plus OH negative. So what that means is whatever my concentration of cesium hydroxide is, it's going to be the same concentration as hydroxide because it is a 1-to-1 ratio. Cool, so my first step is to figure out the concentration of cesium hydroxide. So let's see, I've got 9.2 milligrams, so that's 0.0092 grams. Let's see, I should probably figure out my molar mass because I need to figure out the molar concentration. So cesium is 132.91 straight off the periodic table, plus 1 oxygen, plus 1 hydrogen, so plus 16 and 1.01, so it's 149.92 grams per mole. So let's see, I gotta cancel out grams, I wanna end up with moles. Nice, okay, so that's, what did I say? 149.92. 92 grams for every 1 mole, and we see grams cancels to grams. Now I want this in moles per liter, so let's see, I got 22 milliliters. That's fine, and let's see. So I want a 1 on top, I want to put liters on bottom, 1's just a placeholder. So 0.022 liters. And again, it's a 1-to-1 ratio, so you could put 1 mole of hydroxide for every 1 mole of cesium hydroxide if you wanted to, because technically way over here, not an eraser, way over here, this was, where was I there? Moles of cesium hydroxide, so that cancels, that cancels. We're left with moles of hydroxide per liter. So let's go ahead, let's plug that into the calculator. So 0.0092 divided by 149.92 divided by 0.022. So that is apparently a concentration of hydroxide ion equal to 0.002789. 0.02789 moles per liter. Okay, whew, it's a big step, but we're here. Now it's just the same thing that we've done all along. So pOH is just negative log of the concentration of hydroxide ion. So that's 0.00279 moles per liter. Get the old calculator out. Negative log of the answer that I just had. Perfect. So that's going to be 2.5544944427. Let's see, sig digs. I think I'm only allowed 2 sig digs from the original part. Where'd it go? Of the question, because I only had 2 sig digs up here. So that'd be 2.55 as my pOH. Perfect. Now, if I wanted my pH, it's just going to be 14 minus 2.55. So let's see, 14 minus 2.55, nice and easy. That works out to be 11.45. Nice. So it's a bit of a doozy, but it's the same stuff that we've done before. Anyways, I know that this is a bit of a longer one. Time for you to do some practice, folks. The practice, if you haven't already, it's that piece from before. And let's see, page 23, 24, and 25. So page 23 to 25. Realistically, do this until you're comfortable with it. That's sort of what we're looking at there. Anyways, I'll let you go get to it. Thanks for sticking with me here, and we'll see you again soon. Bye for now, Chem 20s.